Oh, welcome folks to Conics sections today. This is going to be a pretty extensive lesson today, so you're going to have to buckle up and kind of focus and pay attention. I hope you guys get this done early rather than waiting for the last second to get this video done. All right, so we have 3 Conics sections that we need to deal with today. All of them are going to be based around the origin. So we're going to look at the basic ones. But there's a lot of stuff involved in each of the 3 conic sections that we're dealing with. All right, so first question is, what are conic sections? Yeah, it's these 3 words down here at the bottom, but what are they and why do we call them conic sections? So, if you were to take 2 cones like this and put them point to point, and if you were to slice them in different directions, so in this case, parallel to the side of the cone, parallel to the side, you would create a parabola with the cut. And I do have physical representations of this that you can take a look at. I have an actual cone that's been sliced. If you were to slice the cone parallel to the base, you would have a circle. We're not going to deal with circles because it's kind of what's called a degenerate conic section. So we're going to deal with, we've already dealt with circles before, so we're not going to deal with it today. If you were to slice the cone at a slight angle from the circle, you would get an ellipse. So it would come in out one side or out the other. And then if you were to do a vertical slice where you would cut both the cones, you would get a hyperbola, which is the bottom looking, it's kind of a parabola, but not really. The bottom piece and the top piece. And if you were to compare on my physical model, you would notice that the parabola and the hyperbola, their arcs are different. The way they arch is actually different. The hyperbola is a lot wider than a parabola is. Parabola gets steep very quickly. Okay, so that's what they are. So now let's look at the equations. And what we're going to look at, really, is the equations of all 3 of these, the parabola, the ellipse, and the hyperbola. So these are our 3 important ones today. Now, some of you might be thinking you already know the equation of parabola, and you kind of do, but you know the function version. What we're looking at now is a new definition to a parabola, a more of a higher level thinking of parabolas, and it's kind of a higher level math here. So here's what a parabola technically is. A parabola is a set of all points in a plane, so like on an XY axis, that are equidistant from a fixed line called the directrix. So right down here, where's my pen at? Right down here is the directrix. It's an invisible line, it's not necessarily there, it's just a guide for the parabola. Okay, so all points are equidistant from the directrix and a fixed point called the focus. So here's the focus, this is the p value, or the value of p. We use the letter p for various reasons that I don't know. This distance between the vertex of the parabola and the focus, the distance is p. Well, so is the distance from the directrix to the vertex. That distance is also p. This particular picture kind of gives everything that we need to know. Any point, if we choose any point out here on the parabola, even if we chose this point out here, the distance from the directrix to this point and the p value, if I called this m and n, the distances, I would know that m equals n by definition of a parabola. Okay, so that's the definition. What I want to look at is the various parts of this. This is going to be the part where you're going to have to probably pause the video. Sorry, I thought these all came up at the same time here. All right, so with the vertex at 0, 0, there are two sets of equations here. The left set, or not equations, there's really only one equation. The first equation for this particular parabola is x squared equals 4py. Remember, p is the distance from vertex to origin, or sorry, vertex to focus. Make this a 0. I typoed that. That's supposed to be a 0. And this is also supposed to be a 0. Darn it, I forgot to change some things here. Those are all zeros. That's for later, the HK. That's for later. Okay, so the left column here are for all the parabolas that look like this. They open up or they open down. Now here is where we start looking into the higher level math. We have never dealt with sideways parabolas. So y squared, if you have a y squared value, it's going to be a parabola that opens to the right or to the left. And here you might understand if this thing on the right-hand side is positive, then it opens up. If it's negative, it opens down. If it's positive over here, it opens to the right, and if it's negative here, it opens to the left. And I'm talking about the 4p here. So one very big difference here is our equation for parabola is going to be the quadratic piece by itself. So notice here it's x squared equals something and y squared equals something. And this is our standard form for parabolas. Okay, so if you need a second, go ahead and pause, write this down. I'm going to go ahead and move forward. On to an ellipse. So in this particular case, the ellipse is the set of all points in a plane, the sum of which, the sum of whose distances from two distinct points called the foci, so two focus points is called the foci for plural, is constant. So if I was to look at just this vertical version here, the vertical ellipse, if I called this distance d and this distance, or actually I said d1 and d2, d1 plus d2 is always constant. It's always the same value. Sorry, let's not use c because we're using c elsewhere. Let's use n. And it doesn't matter where I chose this point on the ellipse, that sum will always be the same. So if I chose this point down here, this distance and this distance, the sum would still be this n value, whatever it might be. Okay, so you'll notice some things on these pictures, pictures of which you will want to have drawn. Notice that I gave equations with both pictures. Actually, these are the pictures from the textbook, so you can always go back and look at these pictures, but they're ones that you're going to want in your notes. So right in here, it says x squared over a squared plus y squared over b squared. So b is the distance from center to the skinny side, and a is the distance from center to the fat side of the ellipse. So you might pay attention here is a on this left picture. A is actually in both of them, A is the biggest number. Okay, so if A lies on the x-axis, then it has to be under the x. So notice it's x squared over a squared. And then you'll look over here. Since A is on the y-axis, or vertical, it means it has to go under the y value, so y squared over a squared. So notice the variation between the two equations. And the only thing that I really didn't put in this picture, didn't add to this picture, is the idea of a major axis and a semi-major axis. or minor axis, I guess is what we call it. Okay, so the major axis in this case is this line. And actually, let me kind of scratch that. It's actually major axis is this. This is a horizontal major axis, and the length of the major axis is 2a because it goes A to here and A to here. So the major axis, so this is major axis, and the minor axis is in the other direction. And it's likewise over here. The minor axis in this case is horizontal. And the major axis is vertical. But what you'll notice is the major axis, the length is still 2a, and the minor axis, the length is still 2b. And there's reasons you need to know this because you're going to have to be able to solve for a and b eventually when you find equations. All right, so same idea for my ellipses here. I have equations. I have to put on two different pages because the size of them. You'll notice my equation. This is, by the way, this is for, since it's a is underneath the x, this tells me it's a short and fat ellipse. It just automatically. So that's my center, my two focus points, my b values, and my a values. Now what we can actually look at here, I didn't discuss this in parabolas because it wasn't necessary. But since this, actually let's come up here. Since this is b and this is a, let me draw an a, and this is c, very interesting little things here is a squared equals b squared plus c squared. So it kind of has this Pythagorean identity here. It's kind of weird. This distance is a. Very interesting here to me. I think it is anyway. But again, that's useful when we try to find a's, b's, and c values given focus points. All right, so, oh, down here, by the way, semi-major, that just means half the major axis. So the major axis is normally 2a. The semi-major is a, which means just half the length. Same thing with semi-minor. And this is supposed to be, man, typos galore here, plus and minus a and plus and minus c, because the foci are on either sides of the origin, and the vertices are on either side of the origin. Going to the next page, please pay attention. I did change the page here. This is plus and minus c, plus and minus a, again. But in this case, notice that the a value is underneath the y, and therefore that tells me automatically that this is a tall, skinny, or vertical ellipse, where again you have your major axis, your semi-major, or your minor axis, and all of your coordinates. This goes with the picture of before, okay? So be very careful when you're looking at this Pythagorean relation, because it's not what you think of when you think of the Pythagorean equation. All right, moving forward to the hyperbola. I know I'm going quickly through here, but that's the beauty of the video. You can pause and rewind whenever you need to. Okay, so for a hyperbola, this is kind of the more difficult conic section, but it's the set of all points in a plane, the difference of whose distances from two distinct fixed points, the foci, is a positive constant. So if I choose a point on this particular hyperbola, anywhere I choose, doesn't matter, the distance from this focus to this focus, so if I called this D1 and this D2, that would tell me that D1 minus D2 is a constant number, some random constant, whatever it ends up being for this particular problem. Now, that's just the definition. This doesn't usually come to play in any of the problems we deal with, but that's just kind of looking at the definition. Same thing with the ellipse. I didn't mention that before. We don't really need this particular definition, but it's how the hyperbola and the ellipse are defined using focus points. All right. What we will notice here are some other extra pieces here. Okay, so the new name that we get, oh, look, it did put transverse. I wasn't paying attention to that. All right, so transverse axis is the axis that goes across through the focal points. It's also called the focal axis, but we like to give multiple names to the same thing. So here we have a transverse axis that's vertical and a transverse axis that is horizontal. Now, here's the big difference for hyperbolas. If it opens left and right, it's x squared minus y squared. Has nothing to do with a and b. If it opens up and down, that means it's y squared minus x squared. Now, with an ellipse, I did mention this. With an ellipse, a is always bigger. So ellipse, a is always bigger than b. But with a hyperbola, a could be bigger than b, or a could be less than b. So it doesn't actually make any difference for the size of a and b. An ellipse is actually defined by whether or not it's defined on the direction where a is bigger than b. But for hyperbola, a is always the number underneath the variable x or y, depending on which direction it opens. So you can see some confusions that might show up a little bit later when we deal with finding equations and that sort of stuff. You'll also notice that there are some dashed lines in here for hyperbolas, and those are actually asymptotes because hyperbolas deal with asymptotes here. All right, so we're going to define that in just a second, what the asymptotes are. You notice that b doesn't really have a big effect on the function itself or the graph of it itself, but the b actually helps us figure out the asymptotes as well. So you kind of take a look here. This first equation, notice that I have x squared over a squared. That's for the ellipse, or sorry, the hyperbola that goes like this. And the foci, again, I missed my plus and minus signs. Sorry about that. The foci are plus or minus c comma 0. And the vertices are plus or minus a comma 0. So vertices are right in here. They didn't use the word in this particular textbook, but the conjugate axis is the b axis. So the b values here. And again, I'm doing semi-transverse and semi-conjugate, so it's only half of the distance. So it's just the center to the a value or center to the b value. And notice here are my asymptotes. Notice it's very important that we know b and a in order to find my asymptotes. And again, focal width is something that we can use when we write equations as well. All right, going to the other version, this is where it opens up or down. And again, I forgot my plus minus. And again, you should have pictures for these already, but I'm just going to draw them in here as well. And you'll notice the Pythagorean relation is actually one that we remember. A squared plus b squared equals c squared. All right, so let's go ahead and look at a few examples here. So let's write an equation. Let's say I gave you a vertex at the origin and a focus at the point 2, 0. So if we were to do a little sketch, I would have a vertex at 0, 0 and a focus at 2, 0, which means because the focus has to go inside the parabola, it opens to the right. And since it opens to the right, I automatically have the equation y equals 4p, or sorry, y squared equals 4px. Because it opens left or right, it's a y squared. And because it opens to the right, it's a positive version. I need to figure out what the p-value is. And the p-value is just the distance from vertex to focus. Well, that distance is 2. Well, that's super nice, right? P is 2, and therefore y squared equals 4 times 2x. So y squared equals 8x. And that would be the equation that would create this graph. Okay, parabolas, pretty simple, not too big of a deal here. Let's go ahead and move on to an ellipse. So again, we have a center at the origin. And for today's lesson, everything's going to be at the origin, right, by the way. The vertex for a parabola and the centers for ellipses and hyperbolas. Oh, I don't actually know if it's an open this way or not. So let's go ahead and try that again. I have this and this. I know I have a center at 0, 0. And I have a major axis length of 6, but that doesn't tell me which direction it lies. But the foci at negative 2, 0 and 2, 0 tell me that it has to open like this. I say open, really I mean lie like this. It has to be a short, fat parabola. Not parabola, ellipse. 2, negative 2. Now, what would these values be? Well, because the major axis has a length of 6, that means my semi-major is 3. Well, that's nice because that means that's 3 and that's negative 3. The distance between those 2 points is 6. So what does this tell us now? This tells us the A value is 3 because that's the distance from center to vertex. It also tells us the C value is 2 because that's the distance from center to focus. But if you look at your equations, we need a B value. And actually, we do need a B squared value. I'm going to hint at that. So I know for an ellipse, I get a Pythagorean identity. A Pythagorean identity of a squared equals b squared plus c squared. So I get 9 equals b squared plus 4, which is 5. Now I don't even care what b is because in my equation I need b squared. All right, so because it opens, or if it lies this direction, this is going to be an x squared plus a y squared. Obviously, all of them are going to look like this. Notice that it always equals 1 as well, by the way. But because it is on the x-axis, the number under the x has to be my a squared, so that's got to be 9. And the number under my y squared has to be the b squared, so that's 5. And hey, there you go. There's your very simple equation. And that's the equation of ellipse. You could actually go on to Desmos, and you can actually graph these things on Desmos. I didn't mention that for parabolas, but you can go and graph sideways parabolas on Desmos. You can graph ellipses on Desmos, and you can graph hyperbolas on Desmos. And speaking of hyperbolas, let's look at an example for this. So we have a center at the origin. So here we go. We have a center at the origin. In this particular case, I guess I'm choosing 3 problems where they all open the same direction. So we have foci at 3 and negative 3 and vertices at -2 and +2. Well, that means I have a picture that looks like this. It opens left and right. And because it opens left and right, what do I automatically know? Well, I automatically know that it's got to be an x squared minus a y squared. Oops. It has to look like this. So I need to know A and B again. I know A is 2 because A is the distance from center to vertex. C is 3, and I need to know B. I actually really want to know what B squared is, right? Because it's B squared in here in the denominator. Okay, so let's do this really quick. I know for a hyperbola, the Pythagorean identity is A squared plus B squared equals C squared. So I get 4 plus B squared equals 9, and B squared equals 5. Sorry, I get the same numbers here, but it's not a big deal. So if I was to write my equation, let's get rid of this thing here. If I was to write my equation, oh, booger. Okay. I know A was 3, sorry, A was 2. C was 3. B was something. 2 squared plus B squared equals 3 squared. B squared is 5. Okay, back to this. I know it has to be x squared over A squared, so it's 4. So you notice that A is not bigger than B in this case. It's very important that we understand that. I mentioned that a minute ago. Minus y squared over B squared, which was 5, equals 1. There's your equation. Ta-da! Not super hard for most of us. Some of us are going to struggle, but I hope we're all there to help each other out. Last set of problems here. I want to find the focus or the foci, depending on the type of problem we're dealing with. First one is y equals -2x squared. All right, so y equals -2x squared. If I was to sketch this a little bit, because it's a negative, it has to open this direction. We do have a vertex at 0, 0. I missed my 0, 0 point, but it's all right. And we have a focus out here. So I need to figure out, and because we know that this is a p-value, I need to figure out p. Oh, I'm sorry, not paying attention to myself here. This is not in standard form. I have to put this in standard form by saying x squared equals -1/2 y. Right? Because I wasn't even paying attention either, and I know somebody else is going to do this as well. So I need to find the p-value. By the way, this picture actually looks like this because I wasn't paying attention to non-standard form. This is going to look like this, and my focus is going to be down here. So I know the standard equation is, where's my eraser? I know the standard equation has to be x squared equals 4py. Well, I hope you guys see that that means that this number has to equal this number. So that's pretty nice. That means -1/2 equals 4p. And if I divide both sides by 4, or if I multiply both sides by 1/4, p is -1/8. And that's actually the distance from the origin down to my focus, which means the coordinate of my focus point is 0, -1/8. That's as easy as that. Next example. I purposely put the problems like this because I want you to make sure you understand what we mean by standard form. So standard form here has a 1 on the equal side, but we don't in this case. So I have to divide everything by 36. So I get 4x squared over 36 plus y squared over 36 equals 1. And then I can reduce this one to get x squared over, 9 plus y squared over 36 equals 1. So you have to look at this and you have to figure out what kind of ellipse is this. It's a plus sign, so it's an ellipse. I know the bigger number is underneath the y squared, so that means it has to be like this. It has to be vertical. It's a very badly drawn vertical picture. Which means my question here is my focal points are going to be right in here somewhere. But now I need to figure out what are my, in order to find that, I need to find, that's a C value. So I need to know what is C. Well, I can find C if I know what A is and I know what B is. Well, that's easy because I have them in my equation. This number under the y squared is A squared, which means A is 6. And this number under the x squared is B squared, so I know that B is 3. Well, in an ellipse, I know that A squared equals B squared plus C squared. So I get 36 equals to 9 plus C squared. C squared is 27 if I did my math correctly. And C is 3 root 3. Well, that found C value, which means my focal points are plus and minus, oops, sorry, not that direction. Because it's vertical, it's 0, comma, plus or minus 3 root 3. There you go, that answers your question. And let's go ahead, one more question really quick. Let's just do the ellipse, or sorry, the hyperbola as well. Let's do the same thing, put it in standard form. So if I divide everything by 16, I get x squared over 4 minus y squared over 16 equals to 1. That means since this is my A value, A is 2. This is my B value, B is 4. Actually, these are the squares, by the way. Okay, so I need to figure out C because that figures out hyperbolas, or for foci. By the way, this is an X version, so it opens like this. And I know that A squared plus B squared equals C squared. So I get 4 plus 16 equals C squared. C is radical 20, which is actually 2 root 5. Man, how simple are these? All right, so my focal points are plus and minus 2 radical 5, comma 0. Okay, so I hope you followed along. I hope you did well on this. It's kind of a little bit of a lengthy assignment, writing equations, looking for focal points, looking for axes and that sort of idea. This first part is super, super long, but it's really, really good. And it'd be really good for a lot of you guys if you just tried a whole bunch of these types of problems. All right? Keep trying to tell you guys are in a higher level math. Let's start thinking like we're in a higher level math and stop thinking like we're in an easy Algebra 1 class. Okay? I'm going to start telling you guys that. We're not in Algebra 1 anymore. All right? So, good luck on this. I will see you guys on Monday. Have fun.